Hey guys, so here are the solutions for the exam 4 homework that I posted. Alright, so the first question is about the bonds. This is polar covalent bonds. Okay, and so that is anything with an electronegativity difference that's bigger than 0, but less than 2. Okay, so we need the electronegativity table to do this. So I'm using the one that was attached to your exam number 3. Okay, it's also in the lecture notes, I think. But so between the CH4 is a tetrahedral carbon with 4 hydrogens on it, and so that means that each bond is a CH bond, and so I'll go 2.5 minus 2.1. Well, that's going to be 0.4, so that is a polar covalent bond because it's bigger than 0 but less than 2. H2O is a hydrogen-oxygen bond, so that's 3.5 minus 2.1. Again, we're going to get a difference that's between bigger than 0, less than 2, so it's 1.4. This CH3 is a few different kinds of bonds. CH3, and then your OH on here. So the CH bond we already calculated, and we already calculated the OH. The only one here that we haven't done is the COH bond. So carbon is 2.5 and oxygen is 3.5. So the difference there would be 1. Okay, so that is also polar covalent. So these two can't be. And then we have chlorine, the element, which is just a Lewis structure like this. Those are the same atoms, so it's going to be 3 minus 3, which is 0. So our answer is D. Okay. The next one, which of the following has a bond that is ionic? Okay, so ionic typically means metal or non-metal, but I need to find something with an electronegativity difference that's bigger than 2, which sometimes metal and non-metals are, and sometimes they're not. H2 has an electronegativity difference of 0, so it's not that. Xef4 means 2 fluorines are attached to a magnesium, so that's going to be 4 for the fluorine, minus 1.2 for the magnesium. I suspect that's our ionic bond because the difference there is 2.8. We already just did water. The difference between hydrogen and oxygen was 3.5 minus 2.1, so it's 1.4. And we just did CH4, so those are definitely not it. So B. Okay. Alright, so the next one is about Lewis structures. So first off, SO2, S is going to be in the middle, and oxygen on either side. My total electron count is going to be, let's see, sulfur's in the same group, so it's 6 times 3 is 18 electrons. Okay. So I guess what we'll do, alright, I know that oxygen likes to have 2 bonds each, so I'm just going to kind of assume that that might be what it wants. And I can also remember that when I draw the 6 valence electrons, I see that 2 pairs and 2 unpairs. So that means that it's looking for, 2 bonds. Since these oxygens are on their end, the only way we can get 2 bonds is if it's 2 the sulfur in the center. And then I'm going to finish filling in the octet for the outside atoms, the oxygens. So right now they've got 2, 4 around them, so I'm going to just go 6, 8. So 2, 4, 6, 8, and 2, 4, 6, 8, like that. Okay, so total that gives us, I think, 16 electrons. 2, 4, 6, 8, 10, 12, 14, 16. That means that I have to add the other 2 to the sulfur, even though that makes sulfur have an expanded octet. Remember that sulfur is capable of doing that, so it's okay. Things like carbon and oxygen are not capable of doing that. They don't have enough protons to kind of account for the extra electrons hanging out. So we wouldn't want that. Alright, the next one is Xef2. So it's going to be, Xe has 8 electrons because it's a noble gas. And F2 has 7 times 2. So we got a total of 22 electrons for our structure. Xe goes in the middle, surrounded by F. And then, I don't know, let's just do single bonds there to start off with, because fluorine only can handle a single bond since it has 7 electrons to begin with. It can only take one more. So there's 8 electrons on the right hand fluorine and 8 electrons on the left hand. So it gives a total of 16 electrons. We need 22 though. So 16, 17, 18, 19, 20, 21, 22. Okay. The next one is carbonate, CO3 2 minus. So the tricky thing about the 2 minus is I have to remember to add that in. So carbon has 4 electrons. I have 3 oxygens, which each have 6. And a 2 minus means that it absorbed 2 electrons from someplace else. So we have a total of 24 electrons here. Okay. We're going to put carbon in the middle with oxygens around. That. Now, right now, the carbon only has 3 bonds, and I know that carbon needs 4 because it only has 4 valence electrons. So I'm just going to pick one of these, and I'm going to make it a double bond. Okay. Alright. That bottom, looks a little squashed. I'm going to try to fix it. Okay, that's better. So now, now that carbon has 4 bonds, that means its octet is full. We're going to fill in some other electrons around it, around the oxygen. Alright, so the oxygen that's on the left here only has 2 electrons, so we're going to complete the octet by adding 6 more. That gives it 8, so that's good. And then the oxygen on the right is the same thing. It's a single bond there, so there's 6 electrons there. So now I have a total of 16 drawn in there, plus the double bond ones, so 16, 18, 20. But we said 24 electrons, so I got to complete the octet for this oxygen by adding the 4 more electrons. Okay. Obviously, we could have put the double bond anywhere in this molecule. It could have been on this carbon, it could have been on this carbon. So it doesn't matter which one you pick or really what the shape of that is. Again, Lewis dot structures don't really tell us shape, they really just give us the domains around the central atom to help us figure out the shape. So don't feel like worried if your double bond was in a different place. There's resonance structures that can be drawn here, so you may end up with slightly different thing. As long as it has 24 electrons and the octet for carbon is satisfied and all the oxygens, then it's good. You can always use formal charge to help you choose if you have concerns about what might be best. Alright, PCl3, so we get a phosphorus in the center and chlorines around it. Okay, and I guess chlorine can really only handle 1 bond, so I'm just going to go ahead and draw those in. We have a total, phosphorus is in group 15, so it's got 5 electrons, and then the chlorines each have 7, so we get 26 here. Okay, so we're going to fill in the octet for each chlorine first. Some of my electrons look more like eyeballs, but you get the idea at least. Okay, so there's 8 around each chlorine, so that means I have 24 electrons right now, so I gotta put 2 more on the phosphorus. Okay, that would mean that the electron geometry of this is tetrahedral, because there's 4 domains. Anytime there's 4 domains, it's always a tetrahedral electron geometry. Alright, so our last one is SF6. So SF6, S is in group 16, so it's 6 plus 6 times 7, because there's 7 valence electrons for fluorine. Alright, so that means we have 48 electrons. Okay. So we put, I guess, the sulfur in the middle, because it's the first one written, and then fluorines all around. And we'll just bond. Again, fluorine can only handle 1 bond each, So we'll do that. And then we'll start filling in. My electrons are looking more and more like lines for some reason. So we want to make sure each fluorine has an octet. Since there's 6 fluorine, if they all have 8 around them, we can figure out we have 6 times 8, which is all 48 electrons. So once we get them all filled in, we don't need to put any on the sulfur. It's already full. Anyway, because right now it's got 12 electrons around it, which is the maximum we can have for an expanded octet. Okay. It's kind of sloppy, but you should draw a neater one where the electrons are obviously right around the fluorines. It's harder on the iPad. Okay, so these are our structures. Now, we need to answer the rest of the question. So doing a structure is just the first part. We need to indicate if it's polar, nonpolar, or ionic. Okay? So, again, this is talking about whether the whole molecule is polar, nonpolar, because it says molecule is polar, nonpolar, or ionic. So when we're thinking about that, a molecular level rather than the bond level in the last question, we need to think about the shape. Okay? Conveniently, that's the next part of the question. So, the shape of a molecule where we have...
Stay outside.
So, if there's a double bond, that counts as one domain because it's 4 electrons that are right in between the sulfur and the oxygen, so that's like one area. There's another domain, and there's another one. So 3 domains. Our electronic geometry has to be trigonal planar because a triangle is the best way to get 3 domains away from each other. So that means this is going to be... So the geometry has to be bent because you have a triangle where the top of it is electrons, and so the bottom part just makes kind of an L shape. So the SO2 must be bent geometry. And bent geometry is always polar because it has those electrons on the top of it. So there's no electrons balancing it on the bottom. Okay. And then we have, next up is Xef4 F2. So we have, let's do this in a different color. We have one domain here, one here. So each pair of electrons on the center atom is a domain. Okay, so there's 3 unbonded and 2 bonded. So 5 total. That means the electron geometry is going to be trigonal bipyramidal. We saw that a lot in the lab. So hopefully you have an image of what that molecule looks like. The 3 unpaired electrons are on the same plane, and the fluorines are on opposite sides from each other. So this makes that makes it a linear geometry, which is completely symmetric. Even the electrons are totally symmetric. They balance each other out, so that means this is nonpolar. All right, so next up, carbonate, CO3 2 minus. This is 3 domains because we have 3 bonding domains here. That means this is trigonal planar. Okay, so it's just a triangle. That's symmetric, okay? And also because of the resonance structure, the double bond character is shared equally, so those bond lengths are exactly the same. So that makes this one nonpolar also. And then here we have PCl3. We said earlier this is a tetrahedral geometry because there's 4 domains. Okay. But one of those does not have an atom on it, so this is going to be trigonal pyramidal, meaning a pyramid with a triangular base. That is always asymmetric, so that means that it's a polar molecule. Lastly, we have our pink one here. So this has 6 domains around it. It's hard to tell because I drew it so sloppy, but if you had more space, you'd see that there's 6 bonding domains, no non-bonding around the center. Remember that it doesn't matter what the outside bits are doing, it's just about the central atom. So if we have 6 domains, that's always octahedral electron geometry, which is symmetric. Okay, so that means nonpolar also.